So we're all pretty familiar with the product rule from calculus. And that says if you take the derivative of a product of functions f of x times g of x, you end up taking the derivative of one of the functions at a time and then summing. So in other words, you get the derivative of f times g plus f times the derivative of g. And that really leads us to an interesting question. And that question is, are there any other operators that obey the same rule? And what I mean by operator is a map from some sort of mathematical structure to another mathematical structure that satisfies a product rule like this. So in other words, d evaluated at f times g is equal to df times g plus f times dg, where perhaps f and g are not functions, but they're some sort of other objects. Well, it turns out that this sort of rule appears all over mathematics. And in this video, I want to show you guys some examples where this appears outside of the general calculus setting. So let's jump into our first example. Our first example is one that I generally give to my linear algebra class. So as you might imagine, it probably has something to do with matrices. And in fact, it does. So we'll start by fixing any n by n matrix M, and then define our map D from the set of n by n matrices to the set of n by n matrices by D evaluated at A is MA minus AM. So in other words, it is the matrix commutator. Sometimes this would be written as these brackets with an M comma A. Now the claim is that this map, D, satisfies this equation down here, which I have now starred. So it satisfies this thing that looks an awful lot like the product rule from calculus. In fact, it looks exactly like the product rule from calculus, just with a little bit different notation. Okay, so let's prove this claim. And this is actually fairly routine calculation. I think would be a good homework exercise for a linear algebra class. So let's take arbitrary, I'll call them F and G, from the set of n by n matrices with entries in R, although you can take these entries to be in any field. And now let's calculate D evaluated at F times G. So if we've got two n by n matrices and we multiply them, we get a third n by n matrix. That's fairly well known. Okay, so by the definition of D, this is equal to MFG minus FGM. Okay, now keeping in mind where we are trying to go, we're trying to go to this right-hand side. We probably want to add and subtract the same thing in order to build these two parts. And that's exactly what we'll do. So just looking at it for a little bit, you'll see that if we subtract FMG and then add FMG, then the overall result is that we've added 0. But we can group these things together and then factor. So let's group it like this. We have MFG minus FMG plus FMG minus FGM. So we'll group the first two terms and the last two terms. And then let's look at these first two terms and notice that we can factor a G out of the right-hand side. That leaves us with MF minus FM times G. Then likewise, we can factor an F out of the left-hand side of these second two terms. That leaves us with F times MG minus GM. But now let's go up here and look at our definition of our D operator. It takes the commutator with M, but that's exactly what we have right here. Let's notice that this guy right here is exactly D evaluated at F, and then we're multiplying that by G. And then this guy right here is exactly F times this D operator evaluated at G. So now looking at the extreme left and right-hand side of the equation, we see that this function or this operator on the set of matrices indeed satisfies this thing that looks like the product rule. Okay, so let's look at another example. Okay, our next example is something that you might see in a Calculus 3 class or a multivariable calculus class. And again, I think it would be a nice homework or maybe group work exercise in such a class. So we'll start by fixing a vector in R3. So for the sake of simple calculation, I've fixed the unit vector I, in other words, 1, 0, 0, although any vector will do. And then we'll define our operator D from R3 to R3 by D evaluated at a vector V, where that's some arbitrary vector in R3, is I cross V. And then our claim, just like before, is that this operator satisfies this thing that looks like the product rule from calculus. So that will build another example of some sort of operator outside of calculus that satisfies this nice product rule. Okay, so let's jump into this. This example is a little bit calculation heavy, so I might skip a couple of steps, but we'll definitely do enough steps so that you have a feel for how the calculations work. Okay, so let's start by setting a vector f equal to a, b, c. So I'm using f and g for our vectors, so it looks a lot like this thing down here or this thing up here, just like I used f and g for our matrices for the same reason. And then likewise, we need a matrix G. So maybe we'll call this x, y, z. Now, what do we need to calculate? Well, we need to calculate f cross g for sure. So let's do that. F cross g. I generally use the matrix determinant method for this. So let's put I, J, K unit vectors in the first row, and then we will lay our vector f in the second row, A, B, C, and we will lay our vector g in the third row, X, Y, Z. Now we'll use cofactor expansion in order to calculate this determinant. So let's see, our I component, which we get from crossing the first column and the first row, will be given by BZ minus CY. So that's our I component. Well, I'll go ahead and rewrite that in standard column vector notation just to skip a step. So BZ minus CY. Okay, good. And then let's see what our J component is. So our J component is related to the determinant of this 2x2 submatrix coming from crossing out the first row and the second column, but we're off by a sign here if you remember the rule for calculating the cross product. So we will get CX minus AZ. So CX minus AZ. And then finally, for our third entry, we get the determinant of the submatrix that we get from crossing off that column and that row. That will be AY minus BX. AY minus BX. So that's our F cross G. Then while we're at it, let's maybe go ahead and calculate D evaluated at F. So let's see, that's going to be 1, 0, 0 cross A, B, C. So we'll use the same kind of strategy. So we have I, J, K, 1, 0, 0, and then A, B, C. And what's nice about this is we only get something non-zero in 2 of the entries. We have a 0 in our first entry. So that's pretty clear because if we cross the first column in the first row, we've got a row of zeros in that subfactor, but that's going to give us a 0 in the determinant. Then let's see, for this guy right here, if we do that crossing, we will get a minus C. And then for our K component, we will get B. So that's our vector F evaluated with this function D. Okay, let's clean up the board. We'll summarize what we have so far, and then we'll point towards how to finish this off. So in the last board, we calculated F cross G. Let's recall that F was the matrix A, B, C, and G was the matrix X, Y, Z. We also calculated D evaluated our vector F. And then likewise, calculating D evaluated at the vector G is pretty similar. Now what we want to do is look at D evaluated at F cross G. And then also we want to look at D evaluated at F cross G plus F cross D evaluated at G. And if these two are the same, then this operator up here satisfies our product rule again. But instead of matrix multiplication, which is what we had in our last example, or function multiplication, which is what we have in calculus, we have the cross product as our operation between two objects. Okay, so let's maybe get into the bones of this calculation, but I'll let you guys fill in the details. Okay, so from what we see here with D evaluated at F and D evaluated at G, it's pretty easy to calculate D evaluated at a vector. Notice it takes the third component, negates it, and turns it into the second component. It takes that second component down to the third component, and the first component becomes 0. So we can use that to calculate D evaluated at this pretty easily. The first entry will be 0, and then the second entry will be the negation of this third entry. So I'm going to write that as bx minus ay. Then our third entry will be the second entry, so that'll be cx minus az. So that's D evaluated at F cross G. Now let's see what we have over here. So this is D evaluated at F, which is 0 minus CB, cross G, which was X, Y, Z. Then we need to add that to F, which was A, B, C, cross D evaluated at G, which was 0 minus Z, Y. Now, all that's left to do is to do these cross products and see that indeed we do build an equality here. So maybe I'll leave this as a little exercise for you guys to check if you're interested. But needless to say, we do get equality. So we've come up with another example where we found the structure of the product rule outside of calculus. This is maybe in the geometry of three-dimensional vectors. Okay, so let's maybe get rid of this and we'll look at a little bit more universal of an example. Okay, so to put a name to the structure that we've been talking about, we have the following definition. So we have D from A to A is called a derivation if D evaluated at A times B is equal to A times D evaluated at B plus D evaluated at A times B, and that's for all A, B in A. And now you might say, well, what is this space A? Well, generally we take A to be something called an algebra, although it could be a little bit more general than that. And then you might say, well, what is this multiplication? Well, it's whichever multiplication comes along with the structure of our algebra A. So as we saw in our first example, the algebra was the set of n by n matrices, and the multiplication was just multiplication of matrices. In our second example, the algebra was the vector space R3, and then the operation was the cross product. So that's pretty interesting because the cross product is non-commutative and non-associative, but we still had a derivation in that space. Finally, in the example from calculus, our algebra would be given by the set of all differentiable functions. And then multiplication is really just multiplication of those differentiable functions. Okay, so now I want to look at the following problem, which is maybe a pretty classic problem, maybe something you would see if you ever took a course on algebras, and that is to classify all derivations on the space of polynomials in one variable. Here I've taken my ring to be R, but really you could have this to be almost anything. Okay, so let's maybe get to this. Let's start by seeing what a derivation might do to a constant. So you probably have some sort of idea just from calculus. So let's start with D evaluated at the constant 1, because that's maybe the easiest one to work with. Notice that's going to be the same thing as D evaluated at 1 times 1 given that 1 is 1 times 1. But that's going to be 1 times d evaluated at 1 plus d evaluated at 1 times 1, because that's a derivation. But that is equal to 2 times d evaluated at 1. So let's look at the equation that we've built. D evaluated at 1 is 2 times d evaluated at 1. That means that d of 1 is equal to 0. Okay, well, what about other constants that are not equal to 1? Well, I'm going to claim that those are equal to 0 when evaluated by d as well. So that means this derivation has that same property that we have with the derivative. The derivative of a constant is 0, but we need to check that. So let's do d evaluated at some constant c. Notice we can write that as d evaluated at c times 1. But now we're going to use a property that d must have that I haven't really talked about yet. And it's a property that all of our examples had and that the normal derivative has. And that is that it's linear. So by linear, I mean it splits up naturally with addition and with scalar multiplication. So I should maybe put that here, but I've kind of left it off because it's obviously true in our examples, and this is the only time we're going to use it. Okay, so that means we can take this c out, and we have c times d of 1, which is c times 0, which is 0. So far, we've seen that d evaluated at any constant is equal to 0. Now let's see what d evaluated at some power of x is. So let's see that d evaluated at x to the n must be equal to d evaluated at x times x to the n minus 1. But now we can apply our derivative rule like this up here. That's what d satisfies. That gives us d evaluated at x times x to the n minus 1 plus x times d evaluated at x to the n minus 1. But that actually gives us a hint of what might be going on here. We can apply our derivative rule to this again, and we'll see that we get x times the derivative of x to the n minus 2 plus x to the n minus 2 times the derivative of x. Well, notice this will multiply into here, and then it will double up with this term right here. And we'll see that we could maybe take this all the way down to the bottom and come up with some sort of rule for this. But perhaps it'd be easier just to state that rule and then prove it with induction. And so that's what we'll do at the next board. Okay, based on some motivating calculations that we had on the last board, we arrive at the following claim. And that is that d evaluated at x to the n is equal to n times x to the n minus 1 times d evaluated at x. You might say, well, what's d evaluated at x? Well, later we'll see that that's actually free to be anything. Okay, let's look at the proof of that. So we'll do this by induction, and maybe our base case will be the n equals 2 case. So let's look at that n equals 2 case. We have d evaluated at x squared. That's clearly equal to d evaluated at x times x. But by this rule over here, that's equal to x times d evaluated at x plus d evaluated at x times x, which is 2x d evaluated at x, which follows this rule that we're claiming. Okay, now let's make an induction hypothesis. So we'll suppose for some k bigger than or equal to 2, we have d evaluated at x to the k is equal to k times x to the k minus 1 times d evaluated at x. And then make our induction step. So that's going to be d evaluated at x to the k plus 1. So we can write that as d evaluated at x times x to the k. Apply our derivation rule. So that's going to give us x times d evaluated at x to the k plus x to the k times d evaluated at x. Now, using our induction hypothesis, we know exactly what this is. This is k times x to the k minus 1 times d evaluated at x. But when we multiply this x in, we get x to the k. And then we've got like terms, which we can add together, leaving us with k plus 1, x to the k times d evaluated at x. And now all that's left to discuss is what the value of this d evaluated at x is. And we'll see this is allowed to be anything in R adjoin x. And so this could be any polynomial p of x in R adjoin x. It's free to be anything. So that means we're ready to write down a definitive answer to this problem. Our goal was to classify all derivations on the polynomials with coefficients in R with one variable, which we called x. Let's recall that we just got done proving that d evaluated at x to the n was n times x to the n minus 1 times d evaluated at x. That should provide a lot of motivation, because this n times x to the n minus 1 is exactly the standard derivative, like from calculus, of x to the n using the power rule. So that means we're ready to write down the final classification. And that goes as follows. Any derivation d on the algebra R adjoin x is of the following form: d equals p of x times d by dx, where that's our standard derivative, where p of x is in R adjoin x. So that could be any polynomial. You might say, well, what is this p of x? Well, p of x is whatever d of x is. So recall that d of x to the 1 power was free to be anything. Now, I want to point out that that means that we have a choice of any polynomial here, but the space of all polynomials has a standard basis, and that would be x to the n. That means we can wrap all of the derivations on this space of polynomials into one object. And that object is called, well, the space of derivations on R adjoin x. And it has a standard basis. That'll be x to the n times d by dx for all n bigger than or equal to 0. And I want to point out that this has a structure all its own called a Lie algebra. And actually, this notion of derivations of an associative algebra being a Lie algebra is a very important notion. Okay, so we've covered a lot of stuff in this video, but I think we've done a good job of answering this question. Are there any operators that obey the same rule as the product rule that you learned in your calculus class? And yes, there are, and there are many different operators that satisfy this rule. And that's a good place to stop.